In January 2011, grainy photographs appeared online showing a strange, angular aircraft conducting taxi tests at a remote Chinese airfield, a fighter jet that looked suspiciously similar to America's F-22 Raptor, the world's most advanced stealth fighter. Western intelligence agencies, which had been tracking Chinese espionage efforts targeting American aerospace technology for years, immediately recognized what they were seeing: China's attempt to copy the F-22 using a combination of stolen secrets, reverse engineering, and indigenous development. What followed revealed both the extent of Chinese espionage and the fundamental limitations of trying to steal technological superiority.
The genesis of desperation. By the early 2000s, China's military leadership faced an uncomfortable reality. The People's Liberation Army Air Force, PLAAF, was at least 2 generations behind American air power capabilities. While the United States deployed sophisticated 4th-generation fighters like the F-15 and F-16 and was developing the revolutionary F-22 Raptor 5th-generation stealth fighter, China's Air Force remained equipped primarily with copies of Soviet designs from the 1960s and 1970s. The J-7, a Chinese copy of the Soviet MiG-21 from the 1950s, still formed the backbone of Chinese fighter forces. The more modern J-10 and J-11 fighters, while improvements, were based on 1970s-era design concepts and technologies. None possessed stealth characteristics, advanced sensors, or the data fusion capabilities that define modern air combat. In any conflict with the United States, Chinese fighters would be detected, engaged, and destroyed before they could effectively respond. The F-22 Raptor, which entered service with the U.S. Air Force in 2005, represented a technological leap that seemed impossible for China to match through conventional development. The Raptor combined stealth technology that made it nearly invisible to radar, supercruise capability, allowing supersonic flight without afterburners, advanced sensors that provided unprecedented situational awareness, and weapon systems integrated through sophisticated avionics. It was, quite simply, the most capable fighter aircraft ever built. "We cannot allow this capability gap to persist," declared General Zhu Qiliang, commander of the PLAAF, during a closed-door meeting in 2006. "If we fight the Americans with our current aircraft, we will be massacred. We must develop 5th-generation capabilities or accept permanent military inferiority." But developing 5th-generation fighter capabilities from scratch would take decades and require mastering technologies China had no experience with: advanced stealth materials and shaping, sophisticated radar and avionics, high-performance engines, and complex system integration. The conventional approach seemed impossible given China's technological starting point and the urgency of the perceived threat. China's leadership made a fateful decision. They would acquire the technology necessary through any means necessary, including industrial espionage, cyber theft, and exploitation of academic exchanges. What followed was one of the most extensive technology theft campaigns in history, targeting American aerospace companies, defense contractors, and government agencies to steal the secrets of the F-22 and related technologies.
The Great Technology Heist. The Chinese espionage effort targeting the F-22 and American stealth technology began in the late 1990s and intensified through the 2000s. The campaign was comprehensive, sophisticated, and remarkably successful at penetrating supposedly secure systems and organizations. In 2007, Chinese hackers penetrated computers at Lockheed Martin, the F-22's manufacturer, and exfiltrated terabytes of data related to the aircraft's design, systems, and manufacturing processes. The intrusion, detected only after months of access, represented one of the largest compromises of classified military information in American history. Follow-up investigations revealed that Chinese intelligence had also penetrated subcontractors working on F-22 components, creating a mosaic of information that provided detailed insights into the aircraft's design. They didn't just steal blueprints, explained a U.S. counterintelligence official in later congressional testimony. They systematically targeted every aspect of our fifth-generation fighter programs – airframe design, stealth coatings, radar systems, engine technology, avionics architecture, manufacturing processes. They were patient, persistent, and highly effective. By the time we detected many of these intrusions, they'd already extracted enormous amounts of information. The stolen information provided Chinese engineers with detailed knowledge of F-22 capabilities and design approaches. They learned about radar cross-section reduction techniques, materials used in stealth coatings, the aircraft's sensor fusion architecture, and countless other technical details that would have taken decades to develop independently. But stolen information alone couldn't produce a working fighter aircraft. China still had to translate blueprints and specifications into actual hardware, which required manufacturing capabilities and technical expertise they didn't fully possess. The aircraft that emerged from this effort, designated J-20, first appeared publicly in January 2011 when photographs showed it conducting high-speed taxi tests at Chengdu Aircraft Industry Corporation's facility. The timing was deliberately provocative. The photos emerged during U.S. Defense Secretary Robert Gates' visit to China, seemingly calculated to embarrass the United States and demonstrate Chinese capabilities. The J-20's appearance immediately sparked debate among Western analysts. The aircraft's configuration bore obvious similarities to the F-22, a twin-engine design with canted vertical stabilizers, internal weapons bays, and stealth shaping, but also showed significant differences. The J-20 was larger than the F-22, had a different wing configuration, and featured canards, forward control surfaces that the F-22 lacked. Whether these differences represented deliberate design choices or reflected China's inability to fully replicate F-22 design was unclear.
The compromised copy. As the J-20 program progressed through flight testing from 2011 onward, its relationship to the F-22 became clearer. Chinese engineers had obviously studied the Raptor extensively and incorporated many design features and concepts. But they had also made numerous compromises, changes, and adaptations, some intentional, others forced by technical limitations. The J-20's larger size was immediately apparent. The aircraft measured approximately 67 feet long compared to the F-22's 62 feet, with a correspondingly larger wingspan and heavier weight. Chinese sources claimed this was intentional, allowing greater fuel capacity and weapons payload. Western analysts suspected it reflected China's inability to produce engines with sufficient thrust-to-weight ratio, requiring a larger airframe to achieve acceptable performance. The engine question was critical. The F-22 used Pratt & Whitney F-119 engines, producing approximately 35,000 pounds of thrust each, with supercruise capability. China lacked equivalent engines. Early J-20 prototypes used Russian-designed AL-31F engines, the same engines powering China's Su-27 derivatives, which provided adequate thrust for flight testing, but were smoky, fuel-inefficient, and lacked the performance characteristics needed for true fifth-generation capability. The J-20's engines are its Achilles heel, noted aviation analyst Andreas Ruprecht, who closely tracked Chinese military aviation development. They've built a stealthy airframe, but they're powering it with 1980s Soviet engines that produce visible smoke trails and lack supercruise capability. It's like putting a lawnmower in a Ferrari. The vehicle looks fast, but the performance doesn't match the appearance. China's attempts to develop indigenous engines for the J-20, the WS-10 and later WS-15, consumed years and enormous resources while producing engines that remained inferior to American equivalents.
The WS-10 variants that eventually powered some J-20s provided adequate thrust but lacked reliability and sophisticated features like thrust vectoring that enhanced F-22 maneuverability. The WS-15, promised to finally match F-119 capabilities, remained in development years after originally projected service dates, with recurring problems suggesting fundamental difficulties with materials science and manufacturing processes. The stealth characteristics represented another area where the J-20 appeared to fall short of F-22 standards. While the J-20 incorporated radar cross-section reduction features, faceted surfaces, internal weapons bays, serpentine air intakes, experts questioned whether China had mastered the sophisticated materials and manufacturing precision required for true stealth. Stealth depends not just on shaping, but on radar-absorbing materials applied with extreme precision, perfectly fitting panels with minimal gaps, and internal structure designed to minimize radar returns. These requirements demand manufacturing tolerances and quality control far tighter than conventional aircraft. Looking stealthy and being stealthy are very different things, explained a former U.S. Air Force officer with experience in stealth aircraft programs. The J-20's external appearance suggests they understand basic stealth shaping principles, but we don't know if they can manufacture and maintain the aircraft to the tolerances required for low radar observability. Based on what we know about Chinese manufacturing quality in other domains, there's reason to be skeptical.
The avionics dilemma. The F-22's most revolutionary aspect wasn't its stealth or speed, but its avionics, the integrated sensor and information systems that provided pilots with unprecedented situational awareness. The Raptor's AN-APG-77 radar could track multiple targets at long range while remaining difficult to detect. Its sensor fusion combined radar, electronic warfare systems, and data links to present pilots with a complete tactical picture. The aircraft's computer systems processed enormous amounts of data in real time, automatically prioritizing threats and enabling one pilot to manage complex combat scenarios. China's efforts to replicate these capabilities faced fundamental obstacles. Chinese electronics and computing technology lagged American standards by at least a decade, particularly in miniaturization, processing power, and software sophistication. While Chinese engineers could steal specifications and architectures from American systems, actually building equivalent hardware and software required an industrial and technological ecosystem China didn't possess. The J-20's AESA, Active Electronically Scanned Array, radar, while impressive by Chinese standards, almost certainly lacked the range, resolution, and low probability of intercept characteristics of the F-27's APG-77. Chinese software engineering, despite rapid improvements, remained weak in the kind of complex real-time systems required for sensor fusion. And China's electronics manufacturing, while adequate for commercial products, struggled with the reliability and performance requirements of military avionics operating in harsh environments. They can build a radar that works, observed a Western intelligence analyst, but can they build one that works reliably for thousands of hours, maintains performance in electronic warfare environments, and integrates seamlessly with other sensors? Based on what we've seen with other Chinese military systems, probably not to F-22 standards. The result was an aircraft that looked externally similar to the F-22, but likely possessed significantly inferior capabilities. The J-20 might achieve adequate stealth from certain angles, but probably not the all-aspect stealth of the Raptor. It might have supersonic capability, but not sustained supercruise. It might carry advanced weapons, but its ability to employ them effectively against sophisticated opponents remained questionable.
The production struggle.
As the J-20 transitioned from prototype to production aircraft beginning around 2016, China faced the challenge of manufacturing the aircraft at scale while maintaining quality. The PLAAF wanted hundreds of J-20s to counter American fifth-generation fighters, but producing complex stealth aircraft in quantity proved far more difficult than building prototypes. Production rates remained slow, perhaps 20 to 30 aircraft annually, far below the rates at which the United States had produced F-22s or was producing F-35s. Each J-20 required extensive hand-fitting and individual attention, suggesting that Chinese manufacturing processes hadn't achieved the precision required for efficient production. Quality control problems reportedly plagued early production aircraft, with issues ranging from poorly fitting panels that compromised stealth to avionics failures that required extensive troubleshooting and rework. The economic cost was staggering. While exact figures remain classified, estimates suggested China invested at least $10 to $15 billion in J-20 development and initial production, enormous sums for an aircraft that likely remained inferior to the F-22 in most measurable categories. The cost per aircraft probably exceeded $100 million, making the J-20 one of the most expensive Chinese military programs ever undertaken. They're paying first-world prices for a second-tier capability, noted a defense industry analyst. The J-20 represents China's best effort, but it's an effort handicapped by technological limitations they can't overcome just by stealing American secrets. You can't steal accumulated expertise, industrial craftsmanship, or the ecosystem of suppliers and subcontractors that makes American aerospace production so effective. The J-20 entered service with PLAAF units beginning in 2017, with the Air Force claiming initial operational capability in 2018. But operational deployments revealed ongoing problems. The aircraft required intensive maintenance, far more than mature fourth-generation fighters, limiting availability rates. Pilot training progressed slowly, hampered by the aircraft's complexity and limited simulator availability. And combat readiness remained questionable, with exercises suggesting J-20 pilots struggled to employ the aircraft effectively in realistic scenarios.
The strategic failure. By the early 2020s, more than a decade after the J-20's first flight, the aircraft's limitations had become apparent. While China had succeeded in fielding an aircraft that looked like a fifth-generation fighter and possessed some advanced capabilities, it had failed to match the F-22's overall effectiveness. The gap was evident in multiple areas. The J-20's engines, even with upgraded WS-10 variants, remained inferior to F-22 engines in thrust, efficiency, and reliability. The avionics, while sophisticated by Chinese standards, lacked the full sensor fusion and situational awareness capabilities that made the F-22 so dominant. The stealth characteristics, difficult to assess from outside, almost certainly fell short of Raptor standards based on compromises visible in the design and known Chinese manufacturing limitations. Most critically, the J-20 program hadn't achieved its strategic objective of closing the capability gap with American air power. By the time J-20s began entering service in meaningful numbers, the United States had hundreds of F-22s and F-35s deployed, with production continuing. The F-35, which had experienced its own development problems, had matured into a capable platform that equaled or exceeded J-20 capabilities in most categories. And American next-generation programs, the NGAD, Next Generation Air Dominance, family of systems, promised to open new capability gaps just as China was struggling to close existing ones. China spent 15 years and tens of billions of dollars to produce an aircraft that's probably inferior to the F-22, which ended service in 2005, summarized a Rand Corporation analysis. By the time the J-20 achieved operational capability, American forces had moved on to more advanced systems. China is perpetually chasing, always 1 or 2 generations behind, despite massive espionage efforts and enormous investment.
the J-20's operational deployments revealed additional limitations. In exercises and training scenarios, PLAAF pilots struggled against American-trained opponents using fourth-generation aircraft, suggesting that pilot training and tactical doctrine lagged hardware capabilities. The J-20's supposed advantage in beyond-visual range combat, where stealth and sensors should dominate, didn't materialize in practice, with Chinese pilots often reverting to visual range tactics where the aircraft's advantages were negated. Maintenance and sustainability problems plagued J-20 operations. The aircraft required far more maintenance hours per flight hour than mature platforms, limiting how many sorties could be generated. Spare parts availability was problematic, with reports of cannibalization, taking parts from one aircraft to keep others flying. And the sophisticated stealth coatings required constant attention, degrading rapidly in operational conditions and requiring expensive reapplication.
The unlearnable lessons. The J-20 story illustrates fundamental truths about military technology development that China's leadership either didn't understand or chose to ignore. Stealing technology provides a starting point, but doesn't confer the accumulated expertise, industrial craftsmanship, and systemic capabilities that turn specifications into effective systems. The F-22 represented not just excellent design, but decades of American experience in aerospace engineering, advanced materials, avionics development, and systems integration. These capabilities couldn't be stolen or reverse engineered, but had to be developed through long-term investment and accumulated experience. Manufacturing precision and quality control were particular weaknesses. American aerospace manufacturers had developed processes and standards over decades that ensured consistent quality even in complex systems. Chinese manufacturing, despite rapid improvement in commercial sectors, struggled with the tolerances and consistency required for stealth aircraft. The result was aircraft that might meet specifications individually, but couldn't be produced consistently at scale with acceptable quality. The software and systems integration challenges proved even more intractable. Modern fighters are flying computers with airframes attached, and the software that integrates sensors, processes data, and manages combat systems is enormously complex. Chinese software engineering capabilities, while improving, lagged far behind American standards in reliability, real-time performance, and handling the vast complexity of fifth-generation fighter systems. Perhaps most importantly, China's top-down authoritarian approach to defense development created systemic problems that technology theft couldn't solve. Engineers who reported problems or suggested that objectives were unattainable risked political consequences, creating incentives to hide difficulties and present optimistic assessments, regardless of reality. This culture of mandatory optimism meant that problems were discovered late, solutions were inadequate, and the final product inevitably disappointed relative to promises. The J-20 program was hobbled from the start by an approach that emphasized theft over development, appearance over substance, and political objectives over technical reality, concluded a Carnegie Endowment analysis. China created an aircraft that looks impressive in photographs and videos, but whose actual capabilities remain far below what the external appearance suggests. The continuing saga. As of the mid-2020s, the J-20 remains in production and continues to be deployed with PLAF units. China claims to have improved the aircraft through successive variants with upgraded engines, better avionics, and enhanced stealth characteristics. But these improvements remain incremental rather than transformational, and the fundamental limitations of the original design and China's technological base continue to constrain what can be achieved. The program's enormous cost, likely exceeding $50 billion when development, production, and life cycle costs are included, represents resources that might have been better invested in capabilities where China possessed competitive advantages or in areas where Western alternatives didn't exist. Instead, China invested massively to produce an inferior copy of an American aircraft, achieving second-place status at first-place costs.
The broader impact on Sino-American relations has been significant. The extensive espionage campaign that enabled the J-20's development poisoned the relationship, leading to prosecutions of Chinese agents, restrictions on technology transfer, and heightened suspicions of Chinese students and researchers in sensitive fields. The economic value of what China stole, estimated at potentially hundreds of billions of dollars in research and development costs, represented one of the largest intellectual property thefts in history. For American aerospace, the J-20 experience validated the need for robust counterintelligence and information security, but it also demonstrated that even extensive technology theft doesn't translate directly to equivalent capabilities. The United States retains substantial advantages in aerospace technology, not because its secrets are well protected, though security has improved, but because accumulated expertise, industrial capabilities, and systemic advantages can't be stolen. The J-20 program continues, with China producing perhaps 30 to 40 aircraft annually and deploying them to operational units. PLAF pilots are slowly gaining experience with the aircraft, developing tactics and procedures for employment. But more than a decade after the program's public revelation, the J-20 remains what it has always been, an impressive-looking aircraft that falls short of the capabilities it was designed to match. A testament to both Chinese ambition and the limits of technology theft as a path to military superiority. The story of China's attempt to copy the F-22 through the J-20 program is not yet finished. The aircraft will continue in service for decades, may be improved through ongoing development, and will represent a capability that China's rivals must account for. But as a strategic program intended to close the gap with American air power, it has failed. China invested enormous resources, stole vast amounts of technology, and produced hundreds of aircraft, yet remains perpetually chasing American capabilities rather than achieving parity or superiority. This failure doesn't mean China will abandon efforts to match American technological technology. If anything, the J-20 experience may drive even more intensive espionage efforts and greater investment in indigenous development. But it does suggest that technological superiority can't be stolen or copied, but must be earned through long-term investment in the foundations, education, research, industrial capabilities, and accumulated expertise that make technological leadership possible. China's attempt to shortcut this process through the J-20 program produced an aircraft that looks impressive in airshow displays, but represents a strategic failure measured against the objectives it was meant to achieve.